Next, we are going to look at, we are still looking at refining the root locus plot. Okay, and this is going to be the second video, or the second part for that. The first one we looked at breakaway and breaking points from the real axis. Now we are looking at the crossing point, the J omega crossing points. So if, for example, we have a system like the one we plotted above here, so let me come up here and pick this system. Okay, copy this, take it down, and then plot it. Okay, paste it here. So this is the root locus we plotted earlier. So you see that it crosses the real axis here. The J omega axis. So this J omega, and then it crosses the J omega axis here. Okay, that's J omega. Of course, you can easily see that the two crossing points form a conjugate pair. Okay, so by computing one, we should be able to find the other. Okay, so how do you find the point where it crosses the J omega axis? Okay. Well, to find the J omega crossing or axis crossing, you must use the Routh-Howes criteria, as we discussed earlier in unit 6, when we were talking about, or unit 5, when we were talking about stability. Okay, so you use the Routh-Howes criteria, and when you use it, what you do is that you force a row of zeros. So you force a row of all zeros, and we said that if you get a row of all zeros, then you form an auxiliary polynomial and solve for the poles of the auxiliary polynomial. Okay, so what we are going to do is we'll form the Routh-Howes criteria, use the Routh-Howes criteria to generate the Routh table, and that is going to have, in the first column, the K is going to appear in 1 or 2 or 3 rows, and then we'll use that K value to force 0 on the rows. Now note that in order for this to work, we have to force an odd power row to 0. Okay, so you force an odd power row to 0. And once you do that, the auxiliary polynomial then is going to be an even polynomial, and then you solve it to find the complex roots. Okay, so, and then that complex roots will then have the crossing point, and you can use that as your J omega crossing point. I think it's better to illustrate this from an example. So let's look at example. Okay, so an example. Let's say that your KGH, that's your open loop transfer function, is given by s plus 3 all over s4 plus 7s cubed plus 14 s squared plus 8 plus k s plus 3k. Okay, so the assumption is that this was some factors we have expanded to get this. So this is the open loop transfer function we are using. We are not using the closed loop transfer function, and I have to drum this on. Okay, if we knew the roots of the closed loop transfer function, we shouldn't have worried ourselves. Okay, so sorry. So no. Sorry. This is actually TS. Okay. Okay. This is TS. Okay. So this is you form the closed loop transfer function. Yes. And then we apply the route highways to the closed loop transfer function, just like we dealt with in the stability. And I have to drum this home. This is the closed loop transfer function. This is not the open loop. Okay. We are using the open loop for the plotting of the root locus, but we are using the closed loop whenever we are dealing with stability. So let this be drummed home. Now, how do we generate the route table for this? Okay, so we can easily write our S4, S3, S2, S1, S0. Okay, and then you can write, so this is 1, 7, 14, 8 plus k, and then 3k. Of course, then we will have 0 here. Oh. Okay, so now if you solve for this, you will get this first column to be 90 minus k, and then this will be 21k. Of course, that will be 0. Then you solve again, you get this column to be minus k squared minus 65k plus 720 all over 90 minus k, then 0 and 0. So what we'll do is, since these two are already zeros, so we have 0 here, 0 here. So what we'll do is we will force this to become 0. And then immediately, this is an odd row, odd power row. So if we force that to be 0, it means we will equate k squared minus 65k plus 720 all over 90 minus k equals 0. And once that is equal to 0, then we have 0, 0, 0. That is the row of zeros. Okay, so this gives k squared minus 65k plus 720 equals 0, or it gives k squared plus 65 minus 720 equals 0. You can easily solve for this, and when you solve, you get two values of k. One will be positive, one will be negative, and the positive is the one we are using because we are dealing with positive gains. So the positive value will be 9.65. So what we'll do is we'll come back to this portion and substitute that here and there. And so the S2, the power S2, so S4, S3 will not change, okay? Or they will change, but we are not even interested. But the S2 then is going to be 90 minus 9.65, okay? And then 21 into 9.65, okay? And 0. So we can easily use that to find our auxiliary equation, and that is going to give us 90 minus 9.65 s squared plus 9.21 times 9.65 equals 0. So our s then is going to be minus 21 times 9.65 all over 90 minus 9.65. Then we'll find the square root of that. So you see that actually this is this whole thing this is positive number, and this is also positive number. So what is under the root sign then becomes negative number because of this. So the answer is going to be J, the roots of these factors here. Okay, so if you solve that, that is going to be J, so plus or minus J 1.59. Okay, so this tells us that the system is going to be crossing at here J 1.59 and this point, which is minus J 1.59. So whenever you need to find the J omega crossing points, you have to, as a matter of necessity, go to the Rat-Harris, use the Rat-Harris stability criteria, because of course the J omega crossing point is the point of breaking from stable to unstable or unstable to a stable. Of course, for the system we have now, it is the point of breaking from stable to unstable. Okay, as K increases beyond the K value of the crossing point, then the system becomes unstable because we get poles on the real right half plane of the real axis. So that is it for this video with an example. Next, we will look at the arrival and departure points for the complex poles.